So welcome everybody. It's a great pleasure to introduce the next plenary speaker of today. It's Carlos Matheus, a good friend, an excellent mathematician from École Polytechnique and CNRS. He works in dynamical systems analysis, geometry, and interaction between these areas. He's also a wonderful speaker, but I will let him speak for himself. So please, Matheus, the stage is yours.
Thank you very much, Paulo, for the nice words for this introduction, and thanks to the organizers, in particular, Patricia Gonçalves and Mario Bess, for the kind invitation to speak in this conference in honor of the 80th anniversary of the Mathematical Society of Portugal. Yeah, it's a great honor to speak here, and it's a pleasure, of course, to see my Portuguese friends. And it's just a pity that I can't be in Portugal right now, but well, I hope I can get back to Terrinha in the near future. And so, yes, I'm going to talk about billiards, and this is basically an excuse to present my research area, which is dynamical systems. And so basically my talk is divided into three parts, which corresponds to more or less the current knowledge or understanding of dynamical systems, which is in three classes. One is the elliptic dynamical systems, the other is the parabolic ones, and the final ones are the hyperbolic. This is not the historical order, but anyway, I divided my talk in these three portions. And so, yeah, so let's start. So this is the program for today. So I'm going to, before talking about billiards, properly speaking, I'm going to review the physical origins. I mean, I'm not a physicist, so I might make mistakes. So please correct me if you see mistakes. But I'm going to at least tell you the historical background for the introduction of billiards. And then, as I told you, I'm going to present in broad terms, the three areas of dynamical systems, which are the elliptic dynamical systems, the parabolic one, and then I'm closing by the hyperbolic ones. And we are going to see that the billiards are rich enough to have examples in each one of these three subfields of dynamical systems. So let's start with the history. So our history starts in 1738 with Daniel Bernoulli. And so Bernoulli proposed what people call today kinetic theory of gases. And so what this means is the following. He said that basically gases are simply a huge number of particles moving in sort of all directions somehow. And then what we call heat is simply the manifestation of the kinetic energy. And so this is why this is a kinetic theory. So heat is the kinetic energy of the moving particles, and this is what we feel. If they are moving faster, more heat we feel. If they are moving slowly, it's colder. And so this is what Daniel Bernoulli proposed as a theory. And then this theory was taken up by the famous physicist Maxwell in 1859 to describe the first statistical law in physics. So before, physics was kind of deterministic, and for the first time, Maxwell stated a statistical law. And he did so by constructing what people today call a distribution, which is the Boltzmann-Maxwell distribution of velocities, which basically gives the proportion of expected molecules having a prescribed velocity. We are going to see that later in a moment. And a few years later, so about 5 years later, Ludwig Boltzmann, which is a very famous physicist, met this paper by Maxwell, and he was very impressed by Maxwell. And then he started a series of works which led to many papers and books on the foundations of what we now call statistical mechanics. And in particular, Boltzmann proved many results and introduced many ideas. For instance, he proved what we call today the H theorem, which is basically saying that when you have a gas distribution, then it evolves in time seeking for the equilibrium, and actually, so equilibrium meaning the Maxwell-Boltzmann distribution. And during this evolution, a certain quantity called the entropy, so this H in the theorem is for entropy, this is a constant which is always increasing. So entropy always increases, and when entropy increases, we are reaching equilibrium state, which is this Maxwell-Boltzmann distribution. So this is in words. Of course, pictures are much better than 1,000 words. So here I took from Wikipedia one distribution of particles, as you can see here, so in a box. And so here is the initial distribution of velocities. So this is the frequency of particles with a given velocity. So this is the velocity, and this is the frequency of particles with a given velocity. And in this case, the Maxwell-Boltzmann distribution is this orange curve here. And as you can see, we are going to let this system evolve. And as the system evolves, you see that the distribution converges quite quickly to the distribution. I mean, of course, it diverges a little bit, but as the time passes, you see that it's matching more and more this curve. So it's cyclically turning, so it starts again, so it restarted. So you see that, for instance, here, it's already matching nicely. Of course, it fluctuates a little bit, it's a statistical law, but you see that we're kind of converging to this orange curve. And so this is the content of this Maxwell-Boltzmann distribution. And so, of course, if you try to understand the true gases, you quickly get into trouble. The equations are quite complicated. And so what people usually do is to simplify the problem. And in particular, what people did in the statistical mechanics was simplifying the problem first by studying what people call ideal gases. And so ideal gases are basically point particles. So the particles have no dimension. And the only interaction that they have is by perfectly elastic collisions, okay, between themselves and with the walls of the room where they are. And so these are the ideal gases. And actually, mathematicians took up this model and actually simplified even a little bit, even more, because even ideal gases are not very simple to study. And so they did the following. They introduced what people call billiards. So what are billiards? So billiards are models of ideal gases, which are themselves models of what happens in statistical mechanics. So billiards are just the same thing as ideal gases, except that since the particles are points, the probability that they interact between themselves is 0. And so you can basically forget about interaction between particles and just think that the particles are interacting only with the walls. And if you do that, you get a billiard. And this is what mathematicians started to do, and well, theoretical physicists also. And we are going to see that even though this idea is quite simple and simplifies, let's say, twice the problem, even this very simple model of billiards contains a lot of surprises. So it's very difficult. So we're going to see that we don't know yet the complete picture for billiards, but still the mathematical motivation is, I mean, the physical motivation for billiards is that it's a kind of second degree simplification of the original motivating problem from statistical mechanics. And so this is what I wrote here, that billiards are really particles just alternate between straight line motions and reflections with the boundary, but not between themselves because they are point particles. So the probability of meeting is 0. Okay, so now, in order to avoid technicalities, I'm going to concentrate myself on planar billiards. So billiards happening on domains of the plane. And sometimes I will allow also the flat torus, so the quotient of the plane by the integral lattice. And so in other words, the screen that you see when you play Pac-Man. So if you enter on the right of the screen, you go out from the left, and if you go up, you get out down. And so a billiard table for me will be a domain which has piecewise smooth boundaries. So it's made out of a finite piece, finitely many pieces of smooth curves on the plane or on the torus. And then there are two dynamical systems that I want to distinguish. One is the billiard flow, so it's the continuous time evolution. So basically, this means that you give me a point on the domain, and you give me a direction, and then I go by straight line with unit speed, unless I hit the boundary, and then I do a specular reflection. So the angle of incidence equals the angle of reflection. And this reflection occurs instantaneously. And there is also what people call the billiard map, which is just, you don't keep track of the entire orbit during your travel in the interior of the table. You just keep the point in the boundary of the domain, the direction, and then you go for the next bouncing point. And since the trajectory is by straight lines, of course, keeping this data of the billiard map suffices to recover the flow. But of course, there are some technicalities when you actually want to prove theorems, but in principle, if you know the billiard map, you know the billiard flow, and so things in theory are the same. But of course, I'm lying, and not a little bit, I'm lying quite a bit, but anyway. So of course, this is the description with pictures, which is much simpler to understand. So I'm picking a point and then a direction on the circle, and then I'm shooting the particle with unit speed, and then after time t, I stop at a new point in a new direction, which I'm calling phi t of p and theta. And so this is the flow. And the billiard map is just, I'm picking in the boundary, and then I'm forgetting about what happens in the middle, and I'm just picking the next point in the next direction. And these systems are very nice because they are what people call area preserving or volume preserving. So actually the billiard flow preserves the Lebesgue measure of this domain. I mean, the Lebesgue measure on the plane times the Lebesgue measure of the circle. And the billiard map preserves a version of this, of the Lebesgue measure, which is just multiplying by a certain density. But if you forget about this function here, it's basically Lebesgue measure. So these systems are very nice, and this is normal because the systems comes from physics. And so they are Hamiltonian, and Hamiltonian systems tend to preserve volumes, and there are conservation of energy and things like that. So this is normal, perfectly normal. And so let me start with the first class of dynamical systems that I promised to describe, which are the elliptic dynamical systems. So the most simple elliptic dynamical system is this circle. And so let's study a little bit what happens in the circle. So in the circle, if you start with a point in the direction, by symmetry, I can always rotate the circle so that my trajectory is horizontal. There is no loss of generality because of the symmetries of the problem. And so I can assume that I'm shooting a particle from this point here in this direction. And so if you measure this angle here between the tangent to the circle and this line, then you can make a elementary Euclidean geometry argument to see that the next bounce happens. So if you measure this angle here between this point, the center, and the new point, what you see is twice this angle. This is a very nice geometric statement. You can check that the arc here is 2 theta if this angle here is theta. And so this means that if you fix theta, you are always turning by arcs of the same lengths, which are 2 theta, determined by the initial data, right? And also these segments are going to be tangent to a circle which is concentric to the initial one. And so if you draw what people call in the dynamical system the phase space, which is just the domain of the billiard map, what you see is the following picture. Here, I'm putting my circle in the boundary. So positions here give me a coordinate living in this part. And here are the angles with the tangent, which vary between 0 and pi. If I orient my circle here, this angle here goes from 0 to pi. And then what I'm saying is that if I fix theta, I'm doing a rotation. I'm never changing my angle actually, because if this is theta and I'm moving by 2 theta, then the next angle is also theta. So the theta coordinate is fixed in this process by the billiard map. And actually I'm moving just the point by a rotation of angle 2 theta. So in other words, each level is rotated by an angle which depends on the height. And so this is a very simple dynamical system. This is the idea of what people call a twist map, because it's kind of twisting or screwing the cylinder. And this is a very fundamental type of map in certain parts of dynamical systems. And so actually I wrote an analysis because actually cylinders are, if I put them on the plane, topologically they are analysis. So actually in the literature, people like to call cylinder or analyze. I mean, topologically they are the same. And so I think the historical name are really twist maps on analyze. But anyway, you pick your perfect topology. But this is the idea. The idea is that the phase space of this system is very simple, it's a cylinder. and the dynamics is just rotating by certain angles which depend on the height. And actually, more interesting enough is that this dynamical system, this portrait, this structure extends to ellipses. And this is thanks to results by Poncelet, which actually is one of the first theorems that we learned in projective geometry and in algebraic geometry, which is called the Poncelet polarism, and which was actually noticed by Birkhoff that it can be applied to get dynamical information. But the result is really related to Poncelet. I'm going to explain what the result of Poncelet is in a moment. But the idea is this following. If you pick an ellipse, now there are three types of orbits. So either you have an orbit which traces a segment which does not pass it through the foci, between the foci. And if it's not the case, then what you see is a very similar picture to the, a picture is similar to this. You are going to be tangent to a confocal ellipse. If you pass through one of the ellipses, then it's funny. You actually, once you pass through one of the foci of the ellipse, then you are going in the next round, pass through the other foci. And not only that, but if you keep doing that, you are going to converge to the major axis. And finally, if you pass between the foci, you are not going to stay tangent to an ellipse, but rather to the other conic, which is a hyperbola. And so, but the structure is kind of the same. And so the picture, so the phase portrait of the billiard map is kind of that. So let me first draw the flow. So I started with some trajectory here, which is not passing through the foci of this ellipse. And then so you see that it's bouncing and making, they are always tangent to this confocal ellipse. If you press through one of the foci, then you see that you are quickly converging to the major axis. And finally, if you pass between the foci, you are going to be tangent to these two green lines, which are confocal hyperbolates. Okay. And so this is actually a consequence of what people call the Poncelet polarism, which says that once you have such a trajectory here, which is tangent to an ellipse, then this kind of trajectory comes in families. Okay. And so if you put all this information together, what you see is the following phase portrait, which is slightly more complicated than the case of the torus, of the circle, sorry. But still, it's not very hard. So what I did here is the following. I took the ellipse, I broke it up at one of the points of the minor axis. I opened it up. And so here is my periodicity. So basically, this is a point in the minor axis. This is the same point. So you should glue this strip if you want to see the correct picture. But I'm opening up just to see better what happens. And then once you open up at the minor axis and you use angles, then you have this structure here. So if the orbit passes away from, not between the foci, then what you see is a trajectory which is a kind of rotation on a circle. Except that this circle is not a rigid circle, it's a deformed circle. So this picture here is diffeomorphic to a circle because it's closing up. And if you put correct parameters, if you parameterize correctly, then the billiard map is really a rotation, which depends, of course, on the ellipse that you are. But it's very close to what happened before. And similar here for the trajectory passing through the foci. And then if you are passing exactly between the foci, then you are moving from one point here and you are slowly moving, traveling along this line to the major axis. Okay, and so this is the picture. But again, it's slightly more complicated, but the idea is that it's not very complicated because for those who know a little bit of physics, they recognize here the phase portrait of the pendulum or simply a harmonic oscillator. So we are in a very familiar field here. So this dynamical system is very nice. And in particular, we understand completely the dynamics because all this makes a foliation, well, a singular foliation because of this point, but this makes a foliation, and restricted to each leaf of this foliation, I know what my billiard map is doing. It's simply rotating. And so I understand very nicely. And this is what people call a completely integrable systems. And so in particular, since things are rotating at the same speed, you see that you get a phenomenon which is called quasi-periodicity, meaning that things are almost repeating. Well, they repeat if you're rotating by rational angles, of course, but if you are irrational, then you tend to get very close to where you are, but not quite. And this is what people call quasi-periodicity. And the justification for quasi-periodicity in our model comes from the fact that we have these boundaries with positive curvature. So basically, positive curvature of the obstacle makes that the orbits, I mean, you see the film in the movie, orbits are trying to get away from them, from each other. The points are trying to create chaos somehow, but then the boundary puts them together, the focused trajectories. And this effect of trying to go away but focusing, trying to go away, focusing, creates a kind of quasi-periodicity, which is the characteristic of elliptic dynamics. And so this is what I wanted to say about elliptic dynamics, that the explanation is that billiards with positive curvature, that they have tendency to focus trajectories, and this creates a kind of almost repetition of the dynamics. And of course, I mean, this is a fascinating subject which has plenty of open problems. And so if you want to pursue the investigation of elliptic dynamics, you should take a look at these keywords. So one of them is caustics. So caustics are these curves which are always tangent to certain types of billiard trajectories. So we saw that, for instance, if the orbit of a billiard is not passing through the foci, they are always tangent to a certain confocal ellipse. And so this confocal ellipse is what people call caustic. And the name comes from the fact that caustic in Greek means burning. And the idea is that if your trajectory were a laser ray, then the fact that you are always tangent to the surface, it would make the surface burn. And so this is the idea, that you are always tangent to this thing, and so it would heat up this confocal ellipse. And so this is the motivation for the name. Another key name here is integrable system that I already mentioned, which means that it's a system where the phase portrait is kind of completely foliated, or at least partially foliated, by curves where the dynamics is very simple, like rotations or things like that. Another thing which is very important is an important conjecture from Birkhoff, which is still open, which claims that the only tables which are completely integrable are, I mean, and whose boundaries are strictly convex. Of course, I mean, I should put some pause. But if you have a table which is strictly convex and whose phase space is completely integrable, then it should be an ellipse. And this conjecture is open. I mean, there is some recent progress on that by people like Avila, Kaloshin, Zeldich, Hezari, and others, but giving kinds of local versions of this conjecture. But the full conjecture is still open despite the years that passed. Another important thing that I already mentioned in the beginning is that the structure of these maps have a name, which is this idea of twist maps. And so this is another keyword if you want to pursue this, if you want to Google on elliptic dynamics, twist maps. Then there is an important name, which is KM theory, which is, as I told you, sometimes you can't hope for a complete foliation of your phase space, but sometimes have partial foliations, which are already very meaningful to understand the dynamics. And this is what this KM theory provides you. And it's KM in honor of Kolmogorov, Arnold, and Moser, and so forth. I mean, I can give you more reference if you wish, but I think that's it for the elliptic part of my talk. So let me move on, if you allow me, to the parabolic dynamics, if there are no questions about that. So let me move on. Now I'm going to talk about parabolic dynamics, which is the second, say, type of dynamical system, which is very different from the previous one. So now what we are doing is to discuss first dynamics on polygons. And so there is a very old dynamical result. I mean, I think it's one of the oldest dynamical results I know, which is a result by Fagnano, an Italian mathematician, who proved the following. If you translate, of course you have to translate because he was stating this in physical terms, etc. But if you translate into modern language, what he proved is the following. You take a billiard, as a billiard table, any acute triangle. Then there is a periodic trajectory of period 3, which is given by the orthic triangle. So what this means simply is that you take the triangle, you take the perpendiculars to the sides, and then these 3 points determine an orbit, which is a billiard table orbit. it. And so, in particular, he proved that any acute triangle has periodic trajectories. And then if you talk about right-angled triangles, Sinai also noticed that these are also interesting because they are related to physics. So the idea is the following. Sinai noticed in the 70s that if you take a very hard wall, two walls, and then you put masses which are moving in a rod, then with masses M1 and M2, and then you just allow collisions between the walls and the particles, then you get a mechanical system whose trajectories are equivalent to the billiard trajectories on this triangle. And so actually, yeah, there are several mechanical systems which can be related to billiards. And so this is why also, I mean, I think people is interested in this kind of billiards in polygons. In particular, the fact that we know that, I mean, it's not hard to build a periodic trajectory in this triangle, which does something like that. It comes here, go there, 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 and back. Since this triangle here has periodic trajectories, you see that in this system, you can place these balls to get periodic configurations, which is not quite obvious, I guess, from this description. Anyway, so this is what happens for right-angled triangles. And now you can ask what happens for general triangles. And the question is that we don't know much. It's kind of funny. I mean, it's a kind of strange situation that despite many years since Fagnano and other mathematicians, there are many basic questions that we don't know. So for instance, there is a nice question which asks for the ergodicity of typical triangles. And then ergodicity means that basically every orbit, the random orbit, equidistributes in the phase space. So basically they are going to spend a time in a given region which is proportional to the area of this region. And there is a prize for this problem, which was promised by Katok on behalf of the Penn State, the math department of Penn State. And there is a 10,000 euros prize for the solution of this problem, which is, yeah, embarrassingly open. Also, another problem which is not very clear is I talked about right-angled triangles. I talked about acute triangles. What about obtuse triangles? And of course, I was hitting this part because it's not clear that all of them possesses periodic trajectories, even though it's widely believed that this should be the case. And as a mathematician, of course, even though we don't have the answer to this basic question here of knowing the existence of a single periodic trajectory, of course, you can extrapolate and ask about the asymptotics of the periodic trajectories of a given size. Of course, I mean, this set could be empty, and so we are talking about the empty set, but yeah, of course, we don't believe that this is empty, and so this is why this question should be meaningful. But there are many basic questions like that about triangles, I mean, and polygons that we don't know. But not, of course, not that there was some progress. I mean, I'm exaggerating, perhaps. We know some answers. So in particular, there is a nice work by Rick Schwartz in 2008, where he proved that if your obtuse angle is not very big, so below 100 degrees, then he can construct periodic orbits, but which becomes more and more complicated. I mean, Fagnano is just orbit of period 3, just 3 bounces, but his orbits becomes more and more complicated as you approach 100 degrees. And this is why he stopped here, because basically to cover the entire possibilities of triangles, he had to add more and more. And there is a lot of computer-assisted calculations here, and so of course he can't handle infinitely many computations in a computer. So yeah, but at least we know that, yeah, there is, if we're not very far from right-angled triangles, we have these orbits, and of course there are more results about these things, but I'm not going to mention them. I'm just going to mention one setting where we know a lot, which is the setting of rational polygons. So what are rational polygons? So rational polygons are polygons whose angles are rational multiples of pi. And this class is understood very nicely because of a connection with algebraic geometry and to translation surfaces. And so what is the idea? The idea is the following. You take a trajectory, say in this rectangle here, so all angles are pi over 2, so certainly meet this condition. And now a nice idea, which goes back to Fox and Keshner and was independently rediscovered by Katok and Zemniakov, is the following. Rather than letting the trajectory reflect, you reflect the table just to keep the orbit straight. And why this idea has a chance to succeed is because the angles are rational. And so the reflection group generated by the sides is finite. It's basically bounded in terms of the denominators of these angles. And so this means that actually, rather than studying a billiard trajectory on this polygon, what you can do is study a straight line flow on a surface, which in this case is our Pac-Man screen, so the torus. You see that the trajectory enters here and then it goes out there and so forth. And what you get by doing this translation between the rectangle and the torus is that on the torus you can compute everything very nicely. In particular, you can prove easily the following dichotomy, that either your trajectory is periodic if the slope is rational, or if the slope is irrational, then it becomes equidistributed. And so you have this nice dichotomy between periodicity and equidistribution just by looking at this picture here, which maybe is not so very obvious to understand if you look at this side. And so this idea was pursued by several mathematicians of this idea of unfolding and relating to what people call translation surfaces. And I mean, translation surface in general is just a family of polygons on the plane whose with pairs of sides which are glued by translations of the plane. And so this is why the name translation surface. And you can check that this data is the same thing as giving yourself a Riemann surface structure plus an abelian differential. So I'm being a little bit technical here, but I'm just saying these big words just to say that if you look from this point of view of Riemann surface and abelian differentials, then you connect quickly with other tools coming from algebraic geometry. And this is what allowed people to make progress on these problems. So in any case, if you unfold a triangle like that, then you immediately start getting rich surfaces. So if you unfold this triangle here, what you get is an octagon after exhausting the entire group of reflections. And here, these labels means that if I enter this side, I should go out here. Okay, so these sides are identified by translations. And so you get a regular octagon if you do this reflection. And this surface here is very different from the torus. Actually, it's a pretzel. So it's a surface of genus 2, if you do the topology. And but still, you have a kind of straight line flow. So harder than the billiard here, you have a straight line flow on this kind of pretzel, of flat pretzel. Well, not completely flat because there are singularities at the corners, but I'm skipping this point. But the idea is that this connection of translation surface and rational billiard allowed to use, as I told you, tools from algebraic geometry and Hodge theory and other things. And this led to an entire field of math, which is called detachment dynamics. And just to give an idea on how powerful this connection is, let me recall the following conjecture by Hardy and Weber from the 80s. So in the 80s, Hardy and Weber, so they are two physicists. So this is not Hardy the mathematician, but this is Hardy from a physicist from Orsay. They consider the following model of Lorentz gases. So we are back to the origins somehow. They consider what people call the Ehrenfest model, which is in honor of the physicists Paul and Tatiana Ehrenfest. They introduced a model of which they call the wing tree model. And the idea is the following. You take the dimensions for a rectangle, say you take two numbers, less than 1, A and B, and then you draw the rectangle, you put the center of the rectangle at an integer point of the plane, so a point of coordinates m and n with m and n integers, and then you repeat, you do that for all integer points. And so in this way, you get an infinite billiard table. And people started doing these drawings, and they started to ask the following question. So at which speed this particle goes to infinity, for instance? Or is it true that for typical orbits, they stay concentrated in a compact part of the phase space? So these kind of questions. And actually, these physicists, they conjecture that the typical particle, so if you pick the typical point in typical direction, this should diffuse, so goes to infinity. And actually, the diffusion rate should be abnormal. So in probability, what usually we call normal when we see things related to the normal law or the center limit theorem. And so this would mean that if you take the log of the distance that you covered between the initial point and the point that you stop at after time t, and you divide by log of the time, if this process were completely random, if this was a random walk, then by the central limit theorem, the distance that you expect is to be about square root of t. And so if you divide the log, what you get is 1/2. And this physicists, they did numerical experiments, and they saw that the number was not 1/2, was something else, but they could not point because the computers were not very good at this time. And then in 2014, 3 mathematicians, so Lecoq, Berdeliev, they proved this conjecture. And not only it's not they were right, but they could compute the diffusion rate. It's 2/3, which is certainly not 1/2. And so this proves this conjecture. And how they did that? Well, they basically took this table and they related by a complicated version of this unfolding process. They related to Riemann surface of genus 5. And so they looked at in the modular space of surface of genus 5 with abelian differentials. And then they related these diffusion rates with what people call Lyapunov exponents. So this is quite beautiful. So basically the idea is that when you are crossing and trying to get far from this region, you are kind of crossing what people call homology cycles in this genus 5 surface. And the way these cycles cross can be coded into a matrix, which is a kind of period matrix somehow. And then the growth of the size of these matrices basically tells you how far this particle is going to infinity. And there is a tool in dynamical systems, which is when you start doing products of families of matrices. So if you have one matrix, to understand this matrix, what you do in linear algebra is to understand eigenvalues. If you have a family of matrices in dynamical systems, so if you try to do relative linear algebra somehow, so linear algebra in families, what you should do is not look at eigenvalues, but rather at Lyapunov exponents. And so the problem is Lyapunov exponents in general are very hard to compute, except that Kontsevich noticed that in this algebraic scenario, you have closed formula for Lyapunov exponents thanks to the Grothendieck-Riemann-Roch formula. And so this is how you get to these 2/3 after putting all these puzzle pieces together. Okay? And so, of course, you can say, well, this system is so simple that maybe there is another explanation which does not involve algebraic geometry, Grothendieck-Riemann-Roch, moduli spaces, and there's maybe 2/3 comes from some simple explanation that you can just, I don't know. The rectangle has 4 sides, so 4 is 2 times 2. I don't know. I mean, you can try to cook up your explanation. And I think that you are not going to succeed because if you make a slight variation of this model by just removing 1 square out of 4, so you take a group of 4, you take 1 out. You take a group of 4, you take 1 out. You take a group of 4, you take 1 out, and it repeats. So for this billiard table, actually, you can apply the same process, I mean, more or less the same arguments. And this was done by Delacroix and Zorich 1 year after the solution of this conjecture. And the diffusion rate is this very complicated rational number. So 491 over 1053, which is less than 1/2 actually, because the numerator is less than 500 and the denominator is bigger than 1000. And so actually by removing this guy, you get, it's counterintuitive. You remove one guy and it gets harder to diffuse. And so probably this means that there is no easy way to get these diffusion rates without going to this technology of Teichmüller dynamics and these links with translation surface and algebraic geometry. But anyway, But this is the point. So there is some diffusion rate. So there is some kind of chaos in particular because things are diffusing, not like in the Brownian motion, because for the Brownian motion, the number should be 1/2, but still there is some diffusion and some chaoticity happening here, which is very different from what happened for elliptic dynamics. And so actually the explanation for this slow chaos, or what people call parabolic dynamics, is that actually you are moving by straight lines. So for a long time, you don't see anything. But then when you see orbits hitting the corners, close to the corners, you see that if one orbit comes to the left of this point, it bounces like that and goes in this direction. And if you are on the right, you bounce here, but you go to the other side. So they get separated. And so it's this accumulation of slow separations close to the corners that slowly create chaos. And so your dynamics is not quite like the elliptic, because there is a slow creation of chaos. Of course, it's slow, but still it's there. And this is the point. So this is the class of dynamical system, which is not elliptic, so it's not completely tame, quasi-periodic, but it's not very chaotic. It's chaotic, but slowly. And so this is an intermediate class. And now I think I'm going for the final class of dynamical systems, which are the hyperbolic ones. And actually, historically, it's the ones that I studied first when I did my PhD at INPA, but I decided to put them last because they are quite complicated. And I'm just going to give some statements, but not discuss much because the discussion can quickly become technical. But the idea is that, the prototype of hyperbolic dynamical system comes from, in our setting, comes from what people call the Sinai billiards. So these are also called the dispersing billiards. And so the idea is that now the boundaries, so before the boundaries were ellipses, so they were convex. Then for the parabolics, they had zero curvature, I had polygons, and now I'm going to make them concave. And what is the point of concavity is that you see that it quickly creates chaos, so separation of orbits. So orbits spread very quickly, because if you see you have a beam of trajectories here, which are very close together, and then because of the curvature of the boundary that is now concave, you see that this orbit here goes in this direction, this one basically gets back by the same way it came, and this one goes very far, so they spread very quickly. So each bounce makes you lose information from where the orbits came from very quickly. And I think this is maybe not so convincing. So I have a little movie here, which is, I have this table, and now I started with a cloud of points. And so this is the histogram of position of points which are passing through this red box. And this is the histogram of velocities. So I started with some configuration of velocities and some configuration of points. And so in the beginning of the movie, the chaos is so quick that I think you could not see. So I'm going to repeat this movie a couple of times. But the idea is the following. You start with a very tiny cloud of points in this red box with very particular velocities. So the angles are very concentrated somehow, and the particles are concentrated. And after a few bounces, you see that the cloud completely spreads. And if you see the final picture, you could not divinate that a few seconds ago they were concentrated in the red box. So this is what I call quick chaos. So let's see this happening. Also, once more. So this starts here. One bounce, two bounces, and then you see that the angles become more and more distributed, and the proportion of particles inside the red box tends to converge to a quantity, which is actually the area of this box relative to the total area of the table. So you see here that it started very concentrated on the box, and then it starts to spread, and then basically the number of particles that you see at any given time is just the area. And the velocities are basically in all directions. So not only on the table, but on the velocity. So it's really what people call ergodicity on the phase space. So it's really distributing on the table and on the velocities. So it's very quick chaos. And in particular, it's closer to Brownian motion in some sense. And in particular, one model that you can do, I mean, of course, the problem of this previous model is that it contains these kinks. And so people, sometimes they complain that these things are not smooth. And so maybe, I don't know, this non-smoothness is just making something complicated. So actually, you can get rid of this non-smoothness by work on the torus. And so this is why, that's why I said in the very beginning that my billiard tables are on the plane or on the torus. And now I'm going to use the torus. So the torus is just this square with identifications here and there. And on this torus, I'm placing two circular domains. So actually, I have these 4 pieces because you should remember that this piece is glued there, this piece is glued there, and this piece is glued there. And so if you glue everything, you get the circle of radius r. So there are 2 circles here in this torus. And then I'm going to call this table the table Q little r, big R on the torus. And then, of course, since the obstacles are concave, these are this is a class of Sinai billiards. And for them, people know quite a bunch of things. In particular, they know that what we saw numerically actually happens, that you have this sensitivity to initial conditions. So basically, points which start together, they quickly get far apart from each other. Moreover, this distribution that we saw here by the end of the video, this equidistribution on angles and the concentration of particles, which is proportional to the area. This is called ergodicity. This was proved by Sinai in his school. Also, we know by more recent results that these things satisfy the central limit theorem, etc. So basically, all kinds of probabilistic results that you have for random walks, you can this system replicates. But still, we don't know everything. In particular, many basic questions we don't knew until recently. And so to close up my talk, I would like to mention these results here, which connects to what I said about polygons, which is the question of understanding periodic trajectories in this figure. And so what happens here is that in this setting, we can now answer the question of counting periodic orbits. And so in particular, we know that, for instance, if you take that table that I drew here, and you set up the big parameter to be 3/8, and the little parameter to be anything between 1/8 and 1/4, then you can prove by combining the results that I got together with Yuri Lima, and then another result by Baladi and Demers, and that result, even more recent result by Bouzy, you can prove that basically the number of fixed points of the mth iterate of the map, so periodic trajectories of length m, this grows exponentially fast with a rate, which is exactly what people call the topological entropy, which is one of the formalizations of Boltzmann's entropy, somehow. The mathematical formulation of one of the mathematical formulations for entropy. And so in particular, this number grows exponentially fast with a very precise rate. And yeah, of course, we are starting to understand better. So Sinai billiards we have many results, but we are, I mean, as all mathematicians, we are not still satisfied with the answer. So there are many, many more questions that we would like to answer. But I think that at least this gives a glimpse of all categories of dynamical systems that we currently know. So the moral here is that there are basically 3 classes that people are studying somehow: the elliptic ones from the side of Km, then these parabolic ones, slow chaos, and then the hyperbolic ones. And then you are trying to cover more and more parts of the dynamical systems area by trying to determine the boundaries between these 3 classes, which is not easy to determine. And so, yeah, so thank you very much. Obrigadinho. And parabéns a SPM pelos 80 anos, 80 mais anos. And while I wait for your questions, let me leave you with a photo of a place in Portugal that I like. Yeah, so now I'm taking questions. Thank you.
Thank you, Matheus.
Yes.
For the very nice talk. And we are waiting for questions. In the meanwhile, let me ask you one. I got curious in this parabolic flows. Parabolic billiards. Is this diffusion rate conjecture to be related with the house of dimension? When you remove these boxes in the model, and somehow it was related.
There are some conjectures like that people is trying to push, and the idea is the following. The idea is that actually there is a funny conjecture that is not fully proved, but people in this area is pursuing this conjecture, which is I think it was a conjecture by Yokos, but which is the following: you can replace the rectangles by other polygonal obstacles, and then try to see what kinds of figures that you get. Mm-hmm. And we know that by moving the obstacles, but by increasing the number, if you take regular polygons and then increase the number of sides, then you converge to a circle. And so you can ask if these numbers that you get for the corresponding billiards are converging to 1/2. So it's not quite the house of dimension question that you had, but still it's, there's some, and this is not known. Even though it would be natural, it's not known if these numbers converge. And I can tell you what the difficulty is. The difficulty is that when you change the shape of the obstacle, I told you that for the rectangles, somehow you do some calculations and you relate to genus 5 Riemann surface, so surface with 5 holes. If you start increasing the number of obstacles, then the topology increases, and then you are trying to control many things. The Lyapunov exponents with increasing genus, and so we can't do asymptotics yet. If the genus were fixed, then we could handle, I guess. But the problem is here is that the genus is increasing at the same time that we're trying to compute asymptotic quantities. So, but it's so it's more. You are right that the shapes are.
The shapes are important, but in another sense, it's
exactly.
some kind of rigidity. Okay.
Exactly, that's the short answer. Yeah. Okay, but this is a very nice question, and it's
Thanks. And you also included by the end a picture of you playing billiard, maybe younger, and in typical billiards you have some sliding effect on the boundaries. So these are not non-conservative. What is known about this? If you include some noise mimicking this sliding effect in the boundary of a billiard, which one of these would be most affected? Well, I have some guess, but I want to know the opinion of an expert. Yeah,
in some sense, if you put this kind of effects on the boundary, this was somehow studied by people. Including not exactly the effect that you mentioned, but similar effects. There is this Galton boards where you kind of allow gravity somehow, and certainly the most affected are the elliptic and parabolic ones. And but they have results. So I think for the Galton boards, so basically where you allow gravity somehow, you're playing in a table which is not on a plane, but higher on slanted ground. And for those, there are results by Chernoff and Sinai. And it's kind of funny because they kind of find a number which is similar to ours. To the number of Delacroix, Hubert-Liliev, but they have 1/3 there, if I remember correctly, not 2/3. But there are a portion of the literature which is dedicated to understanding other types of, other influences on the billiard dynamics. So you can also add moving boundaries somehow. The boundary is kind of shaking, but slowly.
Oh, nice. Yeah. Very nice. Well, we didn't got any other questions in the chat, in the question and answer.
Oh, I saw. Yeah, there is one question by Mario, I guess, in the chat.
But... Oh, there is one. Yes.
Yeah.
Do you believe that the obtuse triangle conjecture can be performed using closing lemma, but destroying the shape of the border of the triangle?
I think so. Yeah, if allowed to destroy the boundary, yes. because then you get some nice push somehow by making hyperbolic bumps, which helps you, definitely.
But still in controlled shape.
Yeah, exactly.
Okay.
Yeah.
Nice. Well, thank you very much, Matheus, for the very exciting talk and this exciting topic. And let me just remind everybody that the other sessions will be open in 6 stages available in the platform just after lunch. So thank you very much.
Thank you.
E aí, espetacular, Matheus.
Obrigado.